I'm Rod Eggert. I'm delighted to be with the group today. Thank you very much to the organizers for inviting me. My role or purpose today is to provide a broad context, the economic or an economic and public policy context for the more detailed geologic focus on critical minerals that is the purpose of this three-day workshop. As a starting point, let me return to a question that Jesse raised at the beginning of his presentation, and that is, what is a critical mineral with an emphasis on the word critical? Now, if we look up the definition of critical in a dictionary, there'll be a definition that sounds something like indispensable or vital. So a critical mineral, one would imagine, is a mineral resource that is indispensable or vital to something. Now, most of the first 83 elements in the periodic table of elements are vital to someone. And so by 83, I'm looking down at bismuth in the lower right-hand corner. The elements from 1 to 83, in other words, are the the options that material scientists and engineers have when developing materials and processes. So with the normal use of the word critical in front of the word mineral, I would say it's not very helpful. Why not just say mineral resources as opposed to critical minerals? So a somewhat narrower definition has come into use in the discussions of critical minerals that starts with indispensability, or as I say here, essential functionality, but also adds difficult substitution and supply chain risks. And so these three aspects of a raw material are necessary to be labeled critical. And this is more or less the definition that has been adopted around the world. It's similar but not identical to the definition that Jesse presented. Now, in many cases, what have been identified as critical minerals or critical materials are used only in very small quantities in a material. And so some people refer to critical minerals as the spices and vitamins of modern engineered materials, in the sense that spices in good French or Italian or Indian food constitute a very small part of the volume or the weight of the material, but yet provide essential properties. Or think of vitamins that we might take in the morning. Small in terms of volume or quantity, but they help with essential properties of our health. Now, here's a list, the draft list that a committee under the White House and led by work at the U.S. Geological Survey have recommended to be included in the 2021 U.S. list of critical minerals. Well, without counting, you can very quickly see that we maybe have narrowed the scope a little bit from 83 elements, but this is only 50. We're down from 83 to 50 elements that are recommended for designation as critical. I note in the bottom here that these are in rank order, starting at the upper left. So gallium is listed as most critical. And then we go down to iridium, over to praseodymium, down to tin, and so on, with the elements appearing after cesium. So cesium, gadolinium, and then holmium through ytterbium are unranked. And these are based on a quantitative assessment that includes both all three definitional characteristics that I described earlier: essential functionality, difficult substitution, and supply chain risks. Note, however, that what is not included, copper. Copper clearly is indispensable or vital for many things, really for all things electric or electronic, and yet it's not on the list, and that is specifically because copper relative to these listed elements have more diverse production, there's significant US output, and therefore doesn't meet the definitional requirements for critical in this specialized sense of the word. Okay, let's move from that definitional or introductory discussion to the economic context. And I start with the tagline, something important as at risk. And this is to remind us or to note that what is critical is situational. And for Tesla, for example, Tesla has moved into mining, as we heard from Jesse, because it's concerned about its supply chain risks. BMW has announced a supply deal with Livent Lithium. So an automobile manufacturer having a strategic arrangement with a raw material supplier because of concerns about supply chain risks or availability in one sense or another. It could be physical availability. It could be concern about volatile prices. And more generally, I would use the quote that Alex King, a material scientist who was the original director of the Critical Materials Institute, and for a number of years, the director of the Ames Laboratory, one of the Department of Energy national labs, who said, what is critical depends on who you are, where you are, and when you ask. Are you talking about the perspective of the world as a whole, or what is important for the manufacturing sector of a national economy, or what is critical from a company like Tesla or BMW, or are you asking what is critical or vital and subject to supply chain risks for a particular technology, which is really the sense of critical that I think Jesse was using earlier. What is critical to emerging energy technologies, the absence of which could put the deployment of the technology at risk. Another statement about the economic context of critical minerals and critical materials. Each element has its own story in the sense that what is a particular concern varies significantly from one situation to another. In some cases, it's lack of supply chain diversity, the single source of failure. In some cases, the single source of failure also is associated with geopolitical risks. In other cases, we're talking about co-production risks, the idea that an element like tellurium is produced as a really minor byproduct from a waste product in the electrolytic refining of copper, and therefore, to some degree, copper market conditions drive the availability of tellurium in addition to market conditions for tellurium. I say risks and opportunities because there actually is quite a bit of unrecovered minor metal in the various process waste streams of other more major metals like copper or nickel or lead and zinc that are opportunities to take advantage of material that's already been partially processed, but now resides in the process waste streams, either of historical mining or ongoing mining and metallurgical processing. In other cases, the barrier to commercialization is technology. Rare earth resources, rare earth minerals are notoriously difficult to separate. The rare earths are 15 to 17, depending on what you consider to be a rare earth, elements that like to be together. But their uses typically are with individual rare earth elements, and getting them separated from one another is technically challenging. In some cases, commercial entry barriers are an important consideration and part of an element story. One of the barriers to entry in rare earth production outside of China is that there's significant excess capacity to produce rare earths in China. Another potential barrier is opaque markets. Many of the minor metals that are considered critical are small, not very, the markets are not transparent. It's difficult for investors to become sufficiently comfortable with publicly available information to be convinced that an investment in this sector is worthwhile. And et cetera, simply meaning that this is not a complete list. Another part of what I think of as the economic context of critical minerals and materials is that the time dimension is often ignored. In some cases, the risk is short-term. It's based on the location and nature of existing production capacity, a single source of failure that puts a customer at risk. That's to some degree or a large part of the discussion with rare earth elements or with the midstream concentration of battery material production in China, as Jesse discussed earlier this morning. But in other cases, what one is concerned about is the long-term availability, not over the next 6 months, couple of years, or even up to a decade, but availability 20 or 30 years into the future. So would there be enough platinum group element to satisfy the dramatically higher needs of the hydrogen economy and fuel cells should that technology take off? And so the word, really a major theme here in all of these aspects of what I call the economic context is the fact that criticality is situational. What is at risk varies from user to user of a material, and one really needs to drill down more deeply than simply labeling something a critical mineral, a critical material. Now, let's consider the energy transitions that have become very important, the critical minerals for the energy transitions. And think about the broad context here. As I think all of us are well aware, demand for some mineral resources will increase quickly and substantially, although at what rate and by how much, we don't really know yet. Supply, if we're thinking about rare earths for magnets in the state-of-the-art electric motors or lithium or other battery materials, we often have supply that is characterized by supply chains that are fragmented, concentrated, small, and opaque. And the concern clearly is that supply may not grow appropriately to meet growing demand. And I use the word appropriately quite specifically to encompass 4 related but somewhat different things. Supply that grows sufficiently in a way that's affordable, that does so in a sustainable manner, meaning with appropriate environmental controls and appropriate awareness of and management of social consequences in mineral development, and responsibly. And so the fear is that lack of appropriate availability will become an obstacle to the clean energy transitions. So which materials are we talking about? Well, we have a number of electronic applications with solar technologies, as well as more mundane power electronics that include things like gallium, indium, selenium, silver, tellurium, and tin. Well, gallium, indium, selenium, and tellurium are all produced as minor byproducts associated with major metals. For magnets and motors, we have certain of the rare earth elements. And so we have rare earths that are important in state-of-the-art magnets, which are essential in the most efficient electric motors, which in turn are important for wind turbines, EVs, and other industrial and household uses. We have energy storage in batteries and a significant number of mineral raw materials, really a very large number, because of the large number of competing battery technologies. Certainly lithium-ion batteries are the battery of choice at the moment, but we have a number of other battery technologies that are lurking in the background, waiting in the wings, so to speak, including solid-state lithium, sodium-ion, flow batteries, which may use vanadium, and others. There may be even a role for lead here, a reemergence of lead when we think about grid scale storage of electricity. Fuel cells, platinum group elements and selected rare earth elements, nuclear power, a big part of the discussion in Glasgow last week and this week, and in turn, demands for cobalt, dysprosium, gadolinium, hafnium, indium, and others. A figure that is similar to what Jesse showed earlier, but this one from the International Energy Agency. Jesse showed a figure from a recent World Bank study, making the point that demand for some mineral-based materials will increase significantly. The International Energy Agency evaluated these mineral resources elements listed on the right-hand side. In the transport sector, as we go from left, the horizontal dimension, we have increasing kilograms per vehicle in the transport sector. Don't try to read the details of the figure. We simply have the conventional car at about 30 and the electric car at more than 200. So roughly a 7-fold increase in the tonnage of a selected set of mineral-based materials. If we look at power generation, the units of the horizontal axis here are kilograms per megawatt hour. The key point to note is that natural gas and coal are at the bottom, 3,000 or less. And then we go increasingly, or we go up in the figure from nuclear to solar PV to onshore wind to offshore wind. We get up to 15,000. So 3,000 to 15,000 in the extreme, significant growth. And it's about supply chains, not just about mining. In the right-hand lower or in the left-hand figure, we have the percentage of world production accounted for by the top 3 countries, in this case at the mining stage. And so we see fossil fuels, oil and natural gas at roughly 40%. And then we look at copper, nickel, cobalt, rare earths, and lithium, at least 45%. And up to more than 80%, depending on the element. And then we go to the midstream or the processing, and a similar picture emerges. We have fossil fuels at the top and mineral resources at the bottom. And we note the very important role that Chinese producers play in the midstream for many of the mineral resources. Okay, so the final part of my presentation speaks to public policy, or the question, what to do. Now, governments have become publicly concerned about this. Here's a headline from The Economist in March earlier this year. Here's the executive order 1 month into the Biden administration. The executive order, not just on critical minerals, but critical minerals in a number of other supply chains that have become quite prominent in public discussions during the period of the pandemic. And as Jesse also noted, this is not a new issue. There was an executive order, actually a couple of executive orders in the Trump administration related not to supply chains generally, but critical minerals more narrowly. And it didn't begin even with the Trump administration, but the momentum behind critical minerals policy, in my experience, began actually reasonably early in the Obama administration. So it's an issue that has transcended the political party of the president. And it's not just a US issue. It's an issue that's been important in many other parts of the world, including the EU. And so what needs to be accomplished is fairly obvious. We need to produce more through enhancing and diversifying primary production. We need to waste less by improving manufacturing efficiency and enhancing recycling and reuse. And we should use less by developing substitute materials or technologies. Now, for any particular critical mineral, the reducing criticality is probably going to focus more on one or the other than all three of these. And you can think of all three of these responses as competing with one another in reducing supply chain risks. Now, the issue for public policy is, well, what's the role for government here as opposed to the private sector? And so in terms of policy approaches, at the risk of oversimplification, let me present two kind of caricatures that are not completely crazy when we think about public policy approaches. The first I will refer to as neoliberal, although there are lots of different definitions of what neoliberal is. I'm using the term to an approach that starts philosophically by relying on private initiative to solve supply chain problems and focus government activities on areas where the private sector by itself systematically fails. And it's essentially a focus of government policy on establishing a framework in which market activities can thrive. And so when distortions to international trade are the problem, work for freer international trade. Focus on education and workforce and development. Focus on information and strategic analysis when opaque markets are a barrier to market responses. Focus government activities on research and development, and innovating, and then commercializing these innovations as a way out of supply chain risk. So activities that complement market activities, but basically beyond that are hands off. The alternative approach or an alternative framework is to think about what some people call industrial policy. Now, again, industrial policy has many different definitions. Here, I'm using it simply to mean a set of government policies aimed at achieving change sooner than if we rely on the more neoliberal approach at the top of the slide. Nothing happens quickly with government policy in the first category, whereas certain government actions can achieve change more quickly, whether it's through stockpiles, government offtake agreements, or domestic content requirements for public purchases, subsidies, tax incentives, loans, loan guarantees, even equity co-financing for critical mineral investments. Now, if we look at two policy documents, one from during the Trump administration and one early in the Biden administration, we see a framework for US policy published in 2019, a federal strategy that has 6 calls to action, which in effect are a broad framework that's I would call it neoliberal primarily. It focuses on research, on the defense industrial base, international trade, improved knowledge of domestic critical mineral resources, and education and workforce development. Whereas more recently, from June of this year, we see a document prepared as part of the Biden administration's executive order, building resilient supply chains, revitalizing American manufacturing, and fostering broad-based growth, which reflects quite a bit of the neoliberal approach from the previous slide, the 6-point call to action. But there's much more industrial policy here in terms of using things like loan guarantees, government funding for early commercial activities. And there seems to be a growing comfort level with more interventionist government policies in raw material supply chains. So That's my talk. I've tried to emphasize the points I've noted here about critical minerals, the economic context and the public policy context. In terms of public policy, I think the real issue is what's the appropriate mix of private and public activities that appropriately complement one another. And as an economist, what I think of is what I focus on are what are the social goals not being met by market activities. And with that, I will stop. Thank you very much for your kind attention. I'll be happy in any remaining time that we have to answer any questions.